also a pretty severe mental fatigue because you're out there for this long period of time, and every action that you take is important. Whether you're just moving from one location to another or you're installing something, you've got to focus on all of that. So imagine everything you do for over 6 hours, you have to be very...
Of all the experiments you've conducted, which is your favorite and why?
Up here, we're not, scientists in where we're trying to discover things, and we're not like in a lab with a Bunsen burner mixing chemicals to come up with the new unobtainium or costoveranium substance. We're up here executing what experts on the ground, their experiments have been designed to do, and we execute the procedures up here. And so, one of the ones that I got to work on a couple months ago was one where we are growing lung tissue, and up here in zero gravity it grows differently, and we were using different substances to go ahead and clean it out as it goes ahead and grows here in microgravity, and then fixing it so it could go down to Earth and be studied. Well, that particular lung tissue was being grown because it is being developed to have cancer-fighting abilities. And we, our previous crew member dubbed it cancer-seeking missiles. And so that was something that was a real world application of something we're doing up here that hopefully will make life a lot better back on Earth.
Yes, sir. Thank you.
Morning, gentlemen. Cadet Iris Yu. My question is for Joe. How did you adapt to live in space, and vice versa? How did you adapt back to life on Earth? Is there great difficulty in doing one or the other?
I think they both have their challenges, and what's neat about coming up here is noticing how quickly the body adapts to being in space. Of course, you have kind of the normal, what you can call space sickness, where your inner ear is not feeling right, the hairs don't know what to do up here in a microgravity environment, so you don't feel so great. Usually my first 24 hours, I'm on the edge of getting sick, not quite getting sick, so not feeling 100%. But once that goes away and the fluid shifting goes back to a more kind of neutral state, it's almost like we were born to be in space. We talk about it often, how we want to get over there, and we know how to push off, we know how to use our feet to hang on to things, and it's just a supernatural feeling. And then going home, when you land, you wonder, how do humans live on this planet? Because, that gravity, I don't know, you learn about gravity in physics, but it's strong after you've been up here for a few months. So even just moving your head and walking is, it's pretty difficult. But again, the human body is pretty amazing. And within, a few days, you're feeling really, really good. You're driving a car within a week. And in about that same time, you're out running outside. So they have their challenges, but the body is amazing how it adapts going in both directions.
Thank you, sir.
Hello, gentlemen. Cadet Michael Howard. My question is for Mark. Can you describe the Kestrel I mission and the role you played in it?
Sure. The Kestrel I mission was to see if there was an inexpensive way to provide imagery at as low a possible level to tactical commanders. My role in it was to, in fact, right behind us, we're in the Japanese module of the space station right now, and right behind us we have an airlock. There's a slide table that comes out. My role in it was to mount that satellite to that slide table and then transfer the satellite into the airlock, and then the ground control teams brought it outside, grabbed it with a robotic arm, and then the next day or two, I can't remember exactly, my job was to photo document and videotape the launching of that satellite from that robotic arm.
Thank you, sir.
Well, I guess our time is up, but I got to tell you something that was very informative. We really appreciate the time that you spent with us. And Randy mentioned the idea about making a touchdown and spiking the football. Rand, I just want you to know you're going to see that a lot when Army beats Navy here on December 13th.
Go Army, beat Navy.
So I just want to leave you one parting message, and from all of us to you, especially to you, Randy, go Army, beat Navy. Ooh-ah! Thanks again for all you do. You're a special people.
And sir, thank you, sir. It's wonderful to hear. Thank you, sir. It's wonderful to hear your voice again, and I really appreciate the privilege to be able to talk to you all today.
Station, this is Houston ACR. That concludes the event.
Thank you all participants. Thank you all participants. With the U.S. Military Academy, station, please stand by while we reconfigure video and audio comm for your deferred release message.
This Week at NASA keeps you up to date. What NASA does, where NASA goes, what NASA finds. From humans living and working in orbit today to future journeys into deep space. From new scientific discoveries about our solar system and the universe beyond, to better understanding our home planet. From improving air travel to developing cross-cutting technologies for future exploration. When you're as busy as we are, a lot can happen in a week. This Week at NASA, on the air throughout the week or online anytime.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
The story of NASA's Langley Research Center is the story of taking what seems impossible and making it reality. It began just 14 years after the Wright brothers achieved the elusive, some said preposterous, goal of powered flight, a goal chased by humankind for millennia. Their 120-foot journey at Kitty Hawk, North Carolina in 1903 broke the impossibility barrier, setting the course for the next century and beyond. The United States invented the first successful airplane, but European countries brought aviation to new heights. From the start, a number of European governments funded aeronautics research, which paid off when World War I broke out in 1914. Even before the war, aviation leaders realized the U.S. was falling behind and pressed Washington to do something about it. So in 1915, Congress authorized $5,000 to create the National Advisory Committee for Aeronautics, the NACA. This little seed, planted in the fertile farmland of Hampton, Virginia in 1917, grew to become NASA Langley, America's first civilian aeronautics research lab and NASA's first center. And it's been reaching for the impossible ever since.
To go to the moon in this decade, not because they are easy, but because they are hard.
The National Advisory Committee for Aeronautics facility began as administrative offices and a wind tunnel building on rural land that the U.S. Air Service wasn't using. The NACA broke ground for the Langley Memorial Aeronautical Laboratory on July 17, 1917. Topographically, it was a swamp, but geographically, it was ideal.
Hampton was really the perfect area for a facility like Langley. The U.S. Army Air Service was already there, so there was already flying going on. And what the engineers liked was the fact that it was a pretty good distance from Washington. So the suits were up there and the engineers had Langley to themselves.
World War I had shown aircraft's need for more speed, power, and agility. Not just in wartime, but for untapped commercial possibilities. It was for that reason Langley was conceived as a truly national laboratory, to benefit aeronautical exploration. From the start, Langley dedicated itself to building the tools, setting the rules, and solving the problems that kept flight from reaching its potential.
At the time Langley was established, the potential for aeronautics was as big as the sky. There was no place to go literally but up. The United States was really far behind Europe in terms of aeronautical research and progress. The Europeans, after all, had been driven by the fear of war and then an actual war, lots of money going into the technology. In this country, not so much. And the founders of the NACA recognized just how important those European labs had been in pushing European aeronautics.
Langley came online as America's first civilian aeronautical research lab in 1920. The NACA's first atmospheric wind tunnel was already at work testing aerodynamic forces that affect aircraft. It was a good beginning, but by no means state of the art. The aerodynamicists knew they needed to do better, a lot better. And they did. 2 years later, in 1922, they powered up a new device no one had ever seen before. The world's first pressurized wind tunnel, the variable density tunnel.
One of the things they did with it early on was to run a whole string of airfoil tests, just all kinds of airfoil shapes. And they published the data in kind of a catalog that was really of revolutionary importance for airplane designers. You could go to the NACA catalog, you could pick out an airfoil that had the characteristics you wanted, and there you go.
These reports, still used by aircraft designers today, kicked off Langley's reputation as a preeminent research facility. The value of Langley's wind tunnels came early. In 1928, Langley engineer Fred Weick used the propeller research tunnel to design a cowling or cover for propeller engines that reduced drag, cooled the engine, and increased an aircraft's flight speed.
And it was those sorts of improvements coming out of the NACA that really laid the foundation for the advance of both military and commercial aviation in this country.
Success followed success. Encouraged by the propeller research tunnel, which was big enough for a full-size aircraft minus the wings, Langley built a tunnel to test entire planes, wings and all. In 1931, Langley opened the full-scale tunnel, which could test at speeds up to 118 miles per hour.
You really can't talk about the history of aeronautical research at Langley without talking about those wind tunnels. As you get into the mid and late 1930s, Langley, on the basis of the airfoil research, the cowling, and all of the other work they were doing, had established itself. The engineers had established themselves as a match for anybody else in the world. The Germans, the English, Langley was right there contributing to the body of knowledge.
And when the winds of war began to blow, Langley's tunnels were ready to serve. Many believed we would never beat Germany's superior air power. And based on how things looked at the end of World War I, that would be a reasonable assumption. But a lot had changed in one generation.
During the war, I think the lights never went out at Langley Research Center. The full-scale tunnel, I mean, you could put a full-scale fighter with a 40-foot wingspan in that tunnel and do really important tests with it.
Those tests were possible in part because of women who filled critically important jobs in machine shops, laboratories, and offices while men were at war.
The Langley Research Center just played an incredibly important role during World War II, as it had in the years leading up to the war.
After the war, the innovations kept coming to increase structural integrity, safety, and speed. But how fast could we go?
Speed was, at that time, one of the things that aeronautics was all about. after all. And Langley, from the days of the NAC cowling and the other advancements, had certainly done its part to build speed. By the late 1930s and during the war, it became clear to engineers, though, that there was a real problem on the horizon.
That problem was the sound barrier. During World War II, pilots noted that in steep dives, as aircraft approached the speed of sound, Mach 1, they would behave differently than at slower speeds. Langley's tunnels would again be needed to solve that problem, but first the tunnels themselves had to change.
The 8-foot high-speed wind tunnel could handle speeds of up to 500 miles an hour. When you get air much faster than that flowing through a normal tunnel, it began to create all sorts of problems with the reaction of the air to the wall of the tunnel, and you weren't getting good data anymore.
In the late 1940s, Langley's Ray Wright, with the support of Division Chief John Stack, experimented with ways to relieve these effects so that testing at transonic speeds could be done. They developed what they called the slotted throat wind tunnel.
You'd always been able to test at supersonic speeds and, of course, at subsonic speeds, but it was in the transonic area where the tunnels had a problem until Langley engineers solved it.
This was the dawn of the supersonic age, where research would push flight beyond the speed of sound. It was time to take some of the testing out of the tunnels. The U.S. Army Air Force teamed up with Langley and Bell Aircraft to develop an experimental rocket engine-powered aircraft, the X-1.
One solution was to design an airplane to go out and gather the data, and that's what the X-1 was.
On October 14, 1947, test pilot Chuck Yeager took the X-1 on its 50th flight and became the first person to break the sound barrier. Mach 1 was not only reachable, but thanks to Langley and others' research, just the beginning. The future was suddenly coming at us faster than sound, and Langley was up for the challenge of the new high-speed frontier.
At the time the X-1 flew through the sound barrier, it meant a couple of things for Langley. While the wind tunnels were still incredibly important and engineers were still doing that work, now there were these new tools, research airplanes. And so subtly, the mission of the NACA and Langley began to change a little bit.
One of the most brilliant innovations sprang from the mind of engineer Richard Whitcomb. It's called the area rule.
The design concept provides for an indentation in the fuselage near the wing. This indentation reduces the drag at transonic speeds and thus allows the airplane to fly faster and farther without an increase in power.
By the mid-50s, the supersonic age gave way to the hypersonic era and the race to achieve speed above Mach 5. Langley's researchers worked with the other NACA centers, the Navy, Army, Air Force, and North American Aviation to design, build, and test the experimental hypersonic X-15. The world's first hypersonic research aircraft made its maiden voyage on June 8, 1959.
Mach 5 is hypersonic. And of course, the most famous hypersonic manned vehicle was the X-15. And again, Langley's involved in helping to think about the aerodynamics of that vehicle and in testing it. I mean, it was an NACA NASA program that really did bridge from the age of the air to the age of space.
The sky was no longer the limit, and whether or not anyone realized it at the time, the space age had begun. As the early X-planes began to scrape the edge of space, Langley aerodynamicists looked even further. The U.S. had much to learn about rockets, and to learn it, Langley turned to one of its up-and-coming engineers.
Well, Robert Gilruth was an engineer, an aerodynamicist, who went to work at the Langley Memorial Aeronautical Laboratory just before World War II. At the end of World War II, he was instrumental in creating the Pilotless Aircraft Research Division. Now, during those early years, they were exploring the flight regime around transonics into supersonic and ultimately hypersonic flight. So it was very much a rocket development organization.
The team's launching of test rockets from Wallops Island, a remote former Navy base on Virginia's eastern shore, was mostly pure research, until the day the mission changed. In October 1957, the Soviets launched the Sputnik spacecraft and stunned the world. The next July, President Eisenhower signed an act to create a space agency. On October 1st, 1958, the 4 NACA research labs, including the newly named Langley Research Center, formed the nucleus of the National Aeronautics and Space Administration. NASA now included a human space program. Langley was its birthplace and became home to America's first astronauts, the Mercury 7.
The Pilotless Aircraft Research Division is assigned responsibility as it is transitioned into something called the Space Task Group for Project Mercury, the first human spaceflight activity. So Langley becomes the centerpiece of the human spaceflight program for the United States. The astronauts are selected, they are unveiled, they are operating at Langley for the first period of the program. They work on the design and research necessary to build the Mercury capsule.
Gil Ruth Group worked through a host of technical issues, like establishing ways to protect astronauts during re-entry and developing simulators to train humans how to work in space. It also created a global communication system to maintain contact with spacecraft. And to streamline operations, NASA's first flight director, Langley's Chris Kraft, applied the concept of something now synonymous with spaceflight: mission control.
That was an idea that goes back to the World Wars, in which flight control is a centerpiece. You have to understand the logistics of movement and how things are going to be operating. All of that can be done from a room, if you will, with communication systems coming in and going out and data coming in and going out. And they modified those ideas from the military and created the modern mission control.
All of these technological advances required mathematical experts. One of the most well-known was Langley's Katherine Johnson. For years, Langley had hired women to operate primitive mechanical calculating machines. Later, those human computers included African Americans, like Johnson, who went on to calculate the trajectory analysis for the first American in space, Alan Shepard. She also verified computer calculations for John Glenn, the first American to orbit the Earth. Her contributions were so great that she was later awarded the Presidential Medal of Freedom. In the 1960s, the space age, born at Langley, took its next giant step, with a little nudge from President John F. Kennedy. Just 20 days after Alan Shepard's historic 1961 flight, the president gives his decision to go to the moon speech.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
It's a technological miracle in many ways. No one's ever even tried this before in terms of reaching the moon. There were 3 options that anyone could think of. The first option was, let's build a really big rocket, let's fly it to the moon, and then let's land a piece of it on the surface. And that sort of direct ascent option was very quickly put off the table because it was just too expensive and difficult to do.
The second option was called Earth Orbit Rendezvous.
You send up multiple spacecraft into Earth orbit. You convene a armada, if you will, in Earth orbit. They assemble a set of vehicles to go to the moon. They go to the moon, they do their mission, then they come back.
But then a less expensive dark horse candidate arrived on the scene: Lunar Orbit Rendezvous.
In fact, it did not have a very strong following in the senior leadership at NASA in the early 1960s. And a Langley engineer by the name of John Hobolt did the math on this, worked out how it could be undertaken successfully and more easily than Earth Orbit Rendezvous.
Hobolt envisioned a modular spacecraft, launched as one unit. As the main capsule orbits the moon, a lander with 2/3 of the crew would detach and go to the lunar surface. Hobolt's idea won out.
And this was an important decision because this would drive all the technology that would be developed to accomplish the moon program. The Apollo spacecraft, the lunar module landing craft, the big Saturn V rocket were all predicated on that decision.
A couple of years later, Langley trained Gemini and Apollo astronauts how to rendezvous and dock 2 spacecraft while in orbit, setting the stage for the Apollo moon landing. But before anything could land on the moon, we had to know its surface. 5 lunar orbiters took images and beamed them back to Langley.
Well, Lunar Orbiter was an interesting program. How do we get the best imagery that we can possibly get from the lunar surface with a spacecraft that's in lunar orbit, with the intention of, first and foremost, finding good landing sites, ones that are safe to land on, but also geologically interesting so that astronauts can get out of the spacecraft, collect samples, take imagery, and do all of the things that they're supposed to do.
The astronauts also had to be trained to fly the last 150 feet to the lunar surface and then move safely and comfortably in the moon's reduced gravity. 24 Apollo astronauts, including the first person on the moon, Neil Armstrong, trained for their missions at Langley.
Landing on the moon is not an easy task. It's virtually impossible to simulate it here on Earth. They built a huge gantry at Langley Research Center, the Lunar Landing Research Facility, which had cables and hooks and all kinds of things, and you could put a vehicle that was a model of the lunar module suspended from this thing.
Having conquered the moon, Langley turned to the next great challenge: the Viking program to Mars. A mission to investigate the planet's atmosphere and surface and to look for signs of life. NASA Langley managed the Viking project and was responsible for the Viking lander system and mission operations.
The history that it had with Lunar Orbiter, in which it was very successful, sort of gets transferred into the Viking landing program.
A mission to Mars is infinitely more complex than landing on the moon. The Viking 1 and Viking 2 spacecraft, each with its own orbiter and lander, would take months to make the half-billion-mile journey to a rocky, cratered planet that has very little atmosphere. When Viking 1 touched down on the Martian surface on July 20th, 1976, it became the first spacecraft to land safely on the red planet and keep operating. Within seconds, it started taking pictures of Mars and itself. What some call the first Martian selfie. Viking was safe on Mars, gathering tantalizing data from another world. The Langley developed technologies that made it possible have continued to shape the robotic exploration of Mars ever since.
It was a very significant coming of age for both NASA and Langley Research Center. Langley was assigned this task and did it beautifully.
By the time Viking 1 blinked out in 1982, the world's first reusable spacecraft, the Space Shuttle Columbia, was starting its 5th mission. It launched on a rocket and returned to Earth like a glider.
Reusable spacecraft goes back to Buck Rogers in the first part of the 20th century. The cartoon strips, the movie serials, the feature films, they all use reusable spacecraft.
Langley's researchers knew about reusable spacecraft from their work in hypersonic gliders and space planes. Beyond testing the preliminary shuttle designs and capturing tens of thousands of hours of wind tunnel data, Langley's engineers also conducted structures and materials tests, evaluated shuttle tire and braking systems, and improved its thermal protection system. From 1981 through 2011, NASA's 5 shuttles flew 135 missions. Its crew transported large cargo to low Earth orbit, launched, repaired, and recovered satellites, and helped build the International Space Station. With astronauts living and working in space since the year 2000, and commercial companies now conducting supply missions to the space station, NASA could focus on deep space travel. With the Red Planet again in our sights, Langley and other NASA centers are working on the Orion Crew Capsule and Heavy Lift Rocket, the Space Launch System, or SLS.
Mars is sort of the big enchilada of places we'd like to go. And I don't think there's anybody in the space community and probably a whole lot of people outside the space community who would like nothing more than to see astronauts set foot on the Red Planet. It's hard to do. There's radiation hazards, there's the microgravity environment that has to be dealt with. All of those are challenges that need to be overcome to undertake a human mission to Mars.
Langley Research is tackling these challenges and many more. Just like the testing of the Saturn V and shuttle designs, SLS models are being tested in Langley's tunnels and with Langley computer know-how. And Langley engineers have led efforts to build a launch abort system designed to carry the crew away in the event of an emergency during liftoff. Versions of the Orion capsule have gone through testing at the same gantry used to train the Apollo astronauts. Splash tests of Orion mock-ups, outfitted with sensors, and some equipped with crash test dummies, will help us better understand what the spacecraft and astronauts may experience when returning home after deep space missions.
One of the things that you have to do is come down in some sort of target area that is within the bounds of the ships that you've got at sea that are going to recover this vehicle. You do not want to leave the astronauts bobbing in the water for too long.
Langley researchers are using all their tools to make sure everything is on track for our journey to Mars. Even as NASA and NASA Langley turn their attention toward other parts of the solar system, scientists never lost sight of planet Earth. Atmospheric science work at NASA Langley began in the early 1970s as an offshoot of its aeronautics research. Langley applied its expertise in tools, methods, and testing toward a science program that would study the impacts of supersonic flight. To understand changes in the atmosphere, scientists first need to measure it. At Langley, some of the earliest measurements started with the 1975 Apollo-Soyuz mission, when astronaut Deke Slayton operated the Stratospheric Aerosol Measurement, or SAM, sensor.
Aerosols are suspended particles or liquid droplets in the atmosphere. Things like soot, dust, black carbon, pollen, those are all examples of aerosols. And though they're really small, they have a big or large uncertainty in the Earth's climate system. NASA Langley has been instrumental in studying aerosols and the processes related to them and understanding their role in the climate system.
The SAM experiment marked the beginning of Langley's space-based studies of aerosols in Earth's atmosphere. Later, more Langley-developed instruments were sent into space. Many were on satellites, like the first Stratospheric Aerosol and Gas Experiment, or SAGE, launched in 1979, part of the family tree of instruments that grew out of the SAM experiment.
The vantage point of space allows us to look at the Earth's atmosphere, its weather, and its climate, to look at various processes ranging from diagnosing our climate, long-range transport, or even improving prediction from our climate models.
Beginning in the 1980s, the space shuttle served as another tool in the Langley Atmospheric Science Toolbox. NASA's first science payload on a shuttle launched on Columbia's second mission. The Langley-developed measurement of air pollution from space instrument helped scientists build a database of atmospheric carbon monoxide levels. These measurements gave scientists a better understanding of pollution and how far it can spread.
The atmosphere is composed of both natural and anthropogenic pollutants. We talk about aerosols and trace gas pollution. These are critical, and we're seeing increases in places like Asia. Meanwhile, we're seeing decreases in other places around the world. So transport and understanding that transport is important to understand the overall climate system and the composition of these pollutants and gases.
The shuttle also carried a Langley satellite-based experiment that measured the planet's overall warming and cooling. In 1984, Sally Ride, the first American woman in space, deployed the Earth Radiation Budget satellite from the Space Shuttle Challenger.
It's important to study the Earth's radiation budget because it has a critical impact on understanding climate change. The sun's energy comes into the atmosphere. It can be absorbed by greenhouse gases. Some of that energy can be reflected. If we end up with an imbalance in our energy budget, we can see warming in our climate system. And that's why the work that's being done at NASA Langley is critical, particularly some of the satellite-based observations.
The Earth Radiation Budget satellite was also carrying an instrument that would take a closer look at the ozone layer. SAGE 2, another in the family of instruments that grew out of the SAM experiment.
The ozone layer, which is a part of the stratosphere, is critical for life on our planet. The ozone layer protects us from harmful UV radiation. Now, in the past, we used ground-based observations and perhaps balloon measurements, but it really gave us point measurements. It's kind of like seeing a tree, but not necessarily seeing the forest. Satellites allowed us to see the true expansiveness of the ozone hole.
Information from Langley satellite instruments provided the most widely used ozone datasets in the 1990s, helping scientists better understand the hole and how to work across borders to repair it. And in February 2017, Langley extended that ozone monitoring legacy with the launch of SAGE 3 to the International Space Station. Another of Langley's tools for looking at the atmosphere is active remote sensing LiDAR technology. Much like radar uses sound waves to take measurements, LiDAR uses lasers. Launched in 2006, the Calypso satellite, a partnership with the French space agency CNES, uses LiDAR to provide new insight into the role clouds and atmospheric aerosols play in regulating Earth's weather, climate, and air quality.
Two of the biggest uncertainties in climate model projections are aerosols and clouds. Clouds can be a net warmer or a net cooler in our climate system, depending on where they're located in the atmosphere. Another key point with clouds is that clouds form on aerosols. Understanding clouds, their formation, and their distribution will take us a long way in closing the uncertainty in those model projections.
Langley scientists have also used LiDAR instruments on board airplanes. It's part of an airborne science legacy Langley pioneered in the 1980s, when scientists first used instrumented planes to better understand the troposphere, the air we breathe.
The troposphere is the lowest layer of our atmosphere. It's the layer that we live in, and we'll never leave unless we are an astronaut or become an astronaut.
Aircraft and the instruments they carry continue to be important to Langley Earth science. Whether it's to measure and track air pollution, help assess Arctic sea ice, or study the movement of greenhouse gases. Even as Langley's Earth monitoring instruments fly around the skies, new Langley satellite instruments are in the works, including a new version of CERES, the Clouds and Earth's Radiant Energy System. Dating back to the late 90s, CERES and its follow-on instruments are devoted to understanding Earth's radiation budget. Langley is also managing the development of TEMPO, the first space-based instrument to monitor major air pollutants across North America hourly during daytime.
NASA Langley is critical for studying the Earth's atmosphere, given its observations and capabilities related to things like atmospheric chemistry, aerosols, clouds, and the Earth's radiation budget. It also hosts the Atmospheric Sciences Data Center. The data from these satellites, aircraft missions, and otherwise will be critical for closing the uncertainty in our climate model projections.
Learning as much as we can about where we are today will tell us where we're heading tomorrow. Of course, sometimes emergencies arise that no one could have predicted. And in many of those cases, the researchers at NASA Langley have risen to the challenge with timely solutions. Wartime is the ultimate national emergency, and in World War II, Langley earned its wings once again. By methodically examining individual warplanes, engineers learned how to squeeze maximum aeronautic efficiency out of each one. It was called drag cleanup. The magic happened in the full-scale tunnel, starting with the Navy's Brewster Buffalo prototype fighter plane.
This Brewster Buffalo is the classic example. They bring in a plane that's not working the way it's supposed to. It's not performing the way the engineers designed. It wasn't going to meet the basic contract requirements. The real achievement of the drag cleanup study was this invention of a new process for quickly evaluating the performance of a particular aircraft design.
By the war's end, more than 30 varieties of military aircraft flew faster because of drag cleanup.
And you cannot overstate how important that was to the performance of these vehicles throughout the Second World War, and really helped give the Allies an edge in their air power.
Langley's engineering also made a difference in civil aviation.
It benefited the nation and the industry by producing amazing aircraft right after the Second World War, airplanes that could fly faster and farther and higher than anything that had ever been designed in human history.
Those new advancements came at a cost. Vibrations that are inconsequential at lower speeds can be catastrophic as planes flew faster. The vibrations, called flutter, could literally shake a plane to pieces.
And then suddenly in 1959, an Electra fell out of the sky, and another one fell out of the sky, and people lost their lives. And this was a profound crisis for the airline industry.
The Federal Aviation Administration ordered tests to find solutions. Industry turned to NASA Langley and its new transonic dynamics tunnel, designed to study the effects of wind gusts and structural vibration on aircraft.
It was a blockbuster test for that tunnel. But what they did in this work was discover the root of the problems. What caused this vibrations? What caused the flutter to occur? And more importantly, how to fix it.
The Langley testing did more than prevent further accidents and save countless lives. It also set the pace for the aircraft industry.
I think one of the really important contributions that Langley made in this particular moment was that it taught industry how to work together productively, how to identify a research problem, how to solve it, and more importantly, it set up a research agenda for decades to come.
Langley's problem-solving expertise was called on again after the 1985 crash of a Delta airliner at Dallas-Fort Worth Airport that killed 136 people. It went down trying to land in a thunderstorm, doomed by a wind shear downdraft, the second such crash in 3 years. The FAA tapped NASA Langley to lead airborne wind shear and microburst detection research.
A microburst is kind of a mini tornado, but in reverse. And wind shear is when those wind currents suddenly shift unexpectedly. Because of these sudden changes, it makes it extremely hazardous for pilots if they're at the point of a flight when they're trying to land the plane. This is when a number of accidents occurred.
Langley developed a system to better understand and analyze these unusual weather conditions.
Langley researchers come up with a numerical scale they call the F factor to help pilots understand the severity of wind shear. That number, this F factor, if you will, is incorporated into FAA regulations today. But it's a great example how one piece of research can have national impact.
Because of NASA Langley research into sensors that warn pilots a microburst is ahead, wind shear accidents in the U.S. have been virtually eliminated. But it's not just outside agencies that rely on NASA Langley's expertise. After Challenger exploded in 1986, Langley engineers tested the solid rocket booster's failed O-rings. Other Langley researchers focused on the booster joints and came up with a whole new design. After Columbia was lost during re-entry in 2003, Langley wind tunnel and computer-based studies of shuttle aero heating helped paint a picture of what happened. Langley then focused its technical strengths on shuttle's thermal protection system, what made it fail, how to inspect it, how to repair it in orbit, and determine when it was safe to fly, even with minor damage.
So after the shuttle accidents, one in the mid-1980s, the other in the early 2000s, NASA Langley engineers worked together to find solutions to incredibly complicated technological problems. They even developed a camera that could inspect the shuttle while it's in orbit. But the most important contribution they made was helping the United States return to space.
And during the shuttle's final missions, Langley researchers took images unlike those ever seen of the shuttle. Thermal snapshots at Mach 20 that may someday be used to create new spacecraft.
Over the past century, NASA Langley has gained an outstanding reputation for its responsiveness to national emergencies. I think the reason it's been so effective is its people. They're resourceful, they're imaginative, they're creative, and above all else, they have the remarkable capacity to reinvent themselves. It's those qualities that make Langley such a national treasure, and it's what augurs well for the future.
From the beginning, NASA Langley has been in the business of shaping the future. First, we conquered the air, then the sound barrier. After that, the moon. Next step, Mars and beyond. While we've celebrated successful Martian landings, starting with NASA Langley's Vikings in the 70s, and more recently, rovers like Spirit, Opportunity, and Curiosity, future missions will require larger craft, bigger payloads, and eventually human explorers. That will demand improved entry, descent, and landing, EDL technologies that must slow a Martian lander from 16,000 miles per hour for a safe and precise landing. Langley's EDL experts developed and built a heat shield sensor that flew to Mars and will help researchers design future spacecraft. Other game-changing Langley inventions for planetary exploration include lightweight inflatable spacecraft heat shields, inflatable habitats, and next-generation rovers that will allow humans to live and work on other worlds. Langley Research Center has already started building the future, using robots to help create new structures. Langley chemists are also developing the next generation of materials, incredibly strong and lightweight, that could have wide-ranging uses in spaceships and everyday life. But Langley has not forgotten its aeronautic roots or its commitment to X-planes. Almost 70 years after Chuck Yeager broke the sound barrier, Langley is working with industry on a supersonic passenger jet that would transform the sonic boom into a neighborhood-friendly sonic thump. Today's and tomorrow's X-planes have progressed to numbers like 43, the fastest air-breathing aircraft. The X-48, a new aircraft concept designed to be greener and more fuel efficient. And the X-57, the first all-electric aircraft. All are being tested or developed at NASA Langley. On a smaller but perhaps even more ambitious scale, Langley engineers are looking at concepts like personal air vehicles and drones that require the development of intelligent autonomous systems that can allow machines to learn and act independently. Other Langley visionary research will explore new ways to better understand our home planet. Langley scientists are developing low-cost, small satellite technologies to observe the climate and air that we breathe. Sensors and instruments on spacecraft, aircraft, and on the ground, combined with computer modeling, will help us better predict and understand conditions here on Earth. and will continue to add to our long-term climate data records, so critical to understanding our planet.
100 years ago, NASA Langley rose from the farmlands of Hampton, Virginia, to become an aerospace research powerhouse. The trajectory of Langley's mission has carried it beyond the sound barrier, beyond our atmosphere, and even beyond the moon. All the while, NASA Langley's advances in materials and atmospheric science are improving life right here on Earth, expanding our knowledge and protecting the planet. Whether pushing the envelope of science and engineering or responding to national emergencies, the people at Langley are already hard at work shaping its next 100 years, transforming science fiction into reality.
Hey, you're watching NASA TV. Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Station, this is Houston. Station, this is Houston. Are you ready for the event?
Houston, this is Station. Houston, this is Station. We are ready for the event.
United States Military Academy. United States Military Academy. This is Mission Control Houston. Please call station for a voice check.
Station, this is Lieutenant Colonel Diana Laux. How do you hear me?
Hi, Lieutenant Colonel. This is Colonel Mark Vanda. Hi, Lieutenant Colonel. This is Colonel Mark Vanda. I hear you loud and clear. How us?
We hear you loud and clear as well. Over. Okay, at this time, I'd like to introduce Colonel Ed Nasons, who's the head of the Department of Physics and Nuclear Engineering, for a few opening remarks.
Well, crew of the ISS, it is really great to see you. Well, thank you for this great opportunity. My name is Colonel Ed Nasons. I'm the head of the Department of Physics and Nuclear Engineering. If you spell out that acronym, PANE, I'm the head of the House of Pain. And you know we have fun with that. Well, first of all, I'd like to say, usually there's a delayed response to that. First of all, let me say we hope that you all had a great Thanksgiving for you and your families. I saw pictures of your Thanksgiving dinner, and I believe I may have had it better with MREs in Afghanistan. Those little cubes, there's just no way you can make those cubes look like a turkey. I think you're pretty brave for trying out that food. Well, in the season of thanks, we certainly thank you for your continued inspiration of cadets, staff, and faculty at West Point and to the world. Mark, you were an inspiration as an assistant professor in the Department of Physics and Nuclear Engineering, and you continue to do so from the International Space Station. We thank you and we thank NASA for what you do every day, advancing technology and pioneering aeronautical travel into space. We thank you for your bravery in accomplishing the ISS mission. We also thank you for the opportunity to ask you questions, knowing just how busy you are every single day. So today we have cadets from our core physics program and our newly created space science major and minor, which we are offering for the first time to the class of 2020. We are teaching 4 new courses in the major to include aeronautics, space science, astrophysics, and astronomy, and integrated with science, engineering, and humanities, will offer a great foundation for our next generation of Army space cadre, and maybe for future astronauts. We're also fortunate to have here today the Dean of our Academic Board, Brigadier General Cindy Jebb. Now, the lecture hall is packed, and we are ready and eager to engage with you. So let me say thanks again. Thanks again for all you do every single day. We appreciate your great sacrifice. You certainly have the right stuff, to steal a cliche, but you represent what right looks like. And we thank you for this great opportunity. So what I'm going to do now is I'm going to turn it over to Lieutenant Colonel Laux, who will introduce the questioners, and we'll get on with the question and answer period. But again, welcome to the House of Pain. It's great to see you. Thank you.
So, gentlemen, we'll begin the question and answer session. The cadets will come up one by one, and we look forward to your responses.
Gentlemen, I'm Cadet Adrian Barraza, and this question is for Mark. Sir, what is your fondest memory of West Point?
My fondest memory of West Point is actually over the summers going to the concerts on the just on the edge of the plain there, hanging out with my family and really enjoying that beautiful place. I know as cadets you don't get to appreciate it quite the same way that assistant professors and professors do, but you really are in an amazing part of the country, and you're very fortunate to be at that place right now.
Gentlemen, this is Cadet Liam Fulton. This next question is for Randy. Sir, my question is,
growing
what is the most
plants like
challenging
Joe
part
did up
about
here,
being an
growing
astronaut?
lettuce. It is amazing. Obviously, as a Marine, the biggest challenge is working with Army people. How much different stuff we do, and you may not have recency of training, but you've got to be able to approach that task, be very thorough on the previous one. So, and if you're on time, great. If you're ahead of the clock, even better. If you're behind, you still got to pay attention and not worry about rushing off to your next task. Different than what you're facing right now, especially for those that are starting out. So that's probably the biggest challenge we face up here on a daily basis. We have such a myriad of things that we do every day, and they're no 2 days are the same, and the tasks are so varied from unloading a cargo vehicle we just grappled last week
living in a
to doing a medical
microgravity environment
experiment on a
affected the
machine that's
physiological
measuring how
processes
much your
of your
muscles
body,
can do,
and what do you do to combat
growing
these effects?
plants like Joe did up here, growing lettuce. It is amazing how much different stuff we do.
I think this is going to be one
and
of
you may not have
the
recency of
toughest
training, but you can
interviews that we've had with these questions you guys are sending us. But of course, some of the big things we're looking at is muscle atrophy and the loss of our bone density. So we work out for a couple of hours every day, which is kind of nice to have that on your schedule. We have resistive exercise, and it feels just like you're lifting weights back at home. We also have a treadmill and a stationary bike. So we use those on a daily basis. We're learning a lot still about the body. We're having some issues with our eyes, so we're studying that as well. The digestive system seems to work pretty well for most of us, so the body adapts pretty well. I think this is going to be one of the toughest interviews that we've had with these questions you guys are sending us. But
gentlemen, Cadet Stephen Scott, this question is for Mark. How did your experiences in the Army, especially overseas, affect your leadership style and the decision to become an astronaut?
That's a great question. The first thing I would say is leadership-wise, my experience taught me that there are lots of acceptable solutions to any problem typically. And by empowering your soldiers to pick the solution that's a feasible one that they're invested in and they chose, you can really get a lot accomplished, and people enjoy executing the plans that they have worked so hard to make up. It's also taught me that we have a lot more potential than we sometimes believe, and especially at your age, there's a limitless possibilities out there for you, and most people, I think, don't maximize that potential, but recognize that don't ever self-limit yourself. Go ahead and keep pushing forward and say yes a lot when those opportunities arise.
Thank you, sir.
everyone. I'm Gay Yehill, and welcome to NASA's Jet Propulsion Laboratory. After 2 decades in space, the Cassini spacecraft has reached the end of its journey at Saturn. Earlier this morning, the spacecraft made its final approach to the giant planet and plunged into Saturn's upper atmosphere, ending this extraordinary mission. But due to the time it takes for radio signals to travel almost 1 billion miles between the ring planet and Earth, the team won't have confirmation that the mission has ended until they see Cassini's signal drop away. The Deep Space Network is monitoring Cassini's signal, as you can see on this DSN Now display. It's being tracked by a 70-meter wide antenna, Antenna 43 in Canberra, Australia. Here's a live picture of the control room on the other side of the world. The DSN team in Australia is keeping a watchful eye on Cassini's final transmission. Meanwhile, it is 4 a.m. here in California. The sun is not up yet, and more than 1,500 Cassini scientists, engineers, alumni, friends, and family have gathered for this moment. The flight team is in the Cassini Mission Control Area. Others have gathered in Von Karman Auditorium here at JPL, and still more are at Caltech in Pasadena. Folks wanted to be together to share this final moment. This is a vigil, but also a celebration of a remarkable mission. This is the last hour of the last chapter of Cassini's grand finale.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1. And liftoff of the Cassini spacecraft on a 1 billion-mile trek to Saturn. We have cleared the tower. Pitch program is in. Full program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
The SOI burn attitude or pointing position, and light up the rockets.
Doppler ahead.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system. For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
Okay, let's do the numbers, the Cassini numbers. The mission has traveled nearly 5 billion miles since launch, executed 2.5 million commands, taken 453,000 plus images, discovered 6 moons, published nearly 4,000 science papers. And it's not done. Cassini is sending home data right now, right to the end. Let's take a look now and talk to Cassini Program Manager Earl Mays about this. After a lineup like that, you have to be impressed.
We are impressed. It's very impressive, and we're very proud of what we've been able to accomplish over the last 13 years at Saturn. It's been awesome.
So a lot of people are asking then, why must we end this mission this way?
Well, really, and if you think about it a little bit, you'll find out we didn't have any choice. Cassini must be disposed of properly. At some point, there are international treaties that require that we can't just leave a derelict spacecraft in orbit around a planet like Saturn, which has prebiotic moons. So we've got to do something about it. We could have sent Cassini away from Saturn, but Saturn was so compelling, so exciting, and the mission that we finally came up with is so rich scientifically that we just couldn't, we had to finish up at Saturn, not someplace else. So the mission really started about 7 years ago. We've been on this path to actually end up right where we are right now in less than an hour.
So let's talk about what's about to happen and kind of walk viewers through what to expect. But let's start with Monday and the kiss goodbye.
Okay.
Can we talk about that?
Can we bring up that first graphic? Let's see what we got here. So this is the last 22 orbits of Saturn, and every one of them is going between the rings and Saturn. Absolutely unexplored territory, fantastic science every time. And what's been also happening is that out there further away is Titan. And every now and then Titan comes by, and you're going to see it come by for one last final kiss goodbye. That was it. It was very quick. You have to, don't blink. But what happened on Monday was that Titan came by and gave Cassini one last little nudge. Took away a few tens of meters per second, slowed us down just enough so that our entry into Saturn in just a few minutes now is absolutely inevitable.
So Cassini's fate is just sealed.
Sealed, absolutely done. There wasn't much we could have done about it before because this thing had been so wired in, but after that Titan flyby, there was absolutely nothing we can do.
So step us through what has happened over this last week then, getting ready for this moment.
Okay, well, because Cassini is still a science machine, really most of what we've been doing is still gathering more science. And so if you look at this graphic up here, we saw there's the Titan, the kiss goodbye on September 11th, and then we turned right back around after flying by Titan, getting a lot of Titan data. We turned around, played all that data back. It's on the monitors on some of our Jedi displays. You can see those. Played back all of the data from Titan, got good views of the north of the lakes and the clouds again. Then Cassini turned back around again for its final set of science observations. And we actually did a little bit of science and a little bit of just nostalgia. We took our last picture of Enceladus, our last picture of Titan, our last picture of the rings and planet, and we took one more look at the propellers and Peggy, the little moon we discovered out in the A-ring. So there's a little bit of science, a little bit of just kind of, last memento photos, and those all got played back beginning yesterday afternoon about 2:45. Cassini turned back for final call to Earth, played all those data back. They're also available on our real-time display. About 1 o'clock this morning, all that data was down on the ground. Cassini then rigged herself up for, if we go back to that timeline just for a moment.
Let's go back.
Can we go back one?
There
Yeah.
you go.
So September 15th, 1:37 down there, that last plot, we actually configured ourselves into a real-time Saturn probe. Everything that comes into the spacecraft goes right back out. So there's no delay, or as little delay as we can make, so that we actually can become an atmospheric sampling mission as we go into the planet. And then, of course, at 4:55 a.m., that's give or take there are a few seconds on that, we will be entering into Saturn's atmosphere.
And let's advance to the next display. This is what's going to be happening within the last hour.
That's exactly right. We came in over the North Pole, just a little bit east from that perspective. Actually, it looks west here, but a little bit over the North Pole. Just before 4 o'clock this morning, we were 60 degrees north. And as you can see, that descent is very rapid. In 20 minutes from now or so, we'll be at 50 degrees north. Then 12 minutes later, 40, and we'll be slowly, not slowly, very rapidly increasing. The 10-degree north latitude impact point is just about where we're going to finish up. And it's going to happen about 5 of 5 this morning local time.
And the last 90 seconds.
The last 90 seconds, this is really where it's all going to be happening. Cassini's not going to even really notice Saturn until the last 90 seconds because it's in free fall around the gravitational body. It's doing its thing and playing everything. But between 70 and 60 seconds out from final impact, it will start to notice the atmosphere. And you can see in this graphic the very tenuous atmosphere starting to experience. Now, Cassini's been fighting the atmosphere before. As a matter of fact, for the last 5 revs, we've been doing that, and it's done very well. But this time, because we're going to go in so deep, there's not a chance that it can fight to hold on to the atmosphere. That atmosphere where we've been fighting it so far is about the same density as the atmosphere that the International Space Station experiences here on Earth. Very thin, but we're going very, very fast.
All right, and we have the animation from the video earlier that sort of helps us envision, although it might be painful to watch.
Well, it's actually, what you're watching this valiant spacecraft, you can see the thrusters coming out active back as it starts to encounter the atmosphere. Those are small thrusters, okay? They just aren't built to fight the kind of torques. And by the way, that's the antenna, the shell trying to point at the Earth. The thrusters just aren't built to handle the kind of atmospheric torque and drag that Cassini's going to experience. But for about a minute, Cassini will hang on. We'll be sampling the atmosphere. We'll be sending the data back as quickly as we can. And then finally, of course, it's going to lose the battle. And within the next minute, we'll be completely and totally vaporized, becoming part of the planet it went to explore.
Just as planned.
As planned. Just exactly the way we've always had it to do. So.
And so for the team, it is bittersweet. I mean, it is sad, but there's tremendous energy here.
There is. I think we're excited because this is exactly the way we always planned this. It's sad that we're losing an incredible discovery machine. That's a loss. But it was always in the plans, and now it's working exactly the way we set it out. The images we've seen from the last few revs and the science we've had from this entire proximal orbit has just been phenomenal. So the real sense here is just, all right, we got it.
You have. What a wonderful tour.
All right. Thank you.
Well, thanks so much for joining us. I'll let you back in the room. I know you want to be back in there. All right. Thanks, Earl. Meanwhile, DSN 43 in Australia is the antenna locked on Cassini signal. And let's check the update display. The expected loss of signal is 4:55 a.m. and that is about 41 minutes away from now.
We've managed to inspire a younger generation of scientists, and they will continue after this is over and after the original investigators are gone to march on for their own challenges for future spacecraft exploration.
Let's look back to what inspired the mission and the day Cassini arrived at Saturn. The Cassini-Huygens mission was a joint effort of NASA, the European Space Agency, and the Italian Space Agency. It was conceived after the Voyager flybys of Saturn, and scientists all over the world insisted they had to go back.
Hello, this is Arthur Clarke, joining you from my home in Colombo, Sri Lanka. Thanks to the World Wide Web, I've been following the progress of Cassini-Huygens from the time it was launched several years ago. As you know, I have more than a passing interest in Saturn, so I'm going to keep my fingers crossed with what Cassini discovers. And who knows, one day our survival on Earth may depend on what we discover out there.
ahead and SWATCOM. The Doppler has flattened out.
Okay, we have burn complete here for the SOI orbit insertion burn. For Saturn's strong gravity pulling us in, SOI burn attitude or pointing direction, and we'll hope to acquire a signal before that turn actually completes. The completion of that turn is around 7:30
Now, the voice you
local.
heard
We may pick up the
arriving,
signal from
announcing
that
the
turn.
arrival
My
of Saturn,
former
June
student,
30th,
Mike Fink,
2004, was the
couple hundred
voice
miles
of
above
Cassini
Earth.
propulsion engineer Todd Barber. Todd served as the team's commentator, and Todd is back today, once again serving as our team commentator in the same mission control room for a much different event. How does it feel, Todd, to be here?
Hi, Gay. Well, it's great to be back. It's kind of cruel to age 13 years in 2 seconds and have to watch that. But what a demonstration of the longevity of this mission. As you and I sat there in 2004, we never dreamt we'd be here in 2017 still talking about Cassini and collecting science data. So I'm just thrilled to be here, even having aged some years since SOI.
Well, Todd, very quickly, we're a couple of minutes behind here. Explain to us why the team has gathered here, even though you had told me that the spacecraft met its fate probably about 3:30 Pacific time out at Saturn, but yet the team is waiting here now and holding vigil. Why is that?
Well, it's that pesky Albert Einstein and his speed of light speed limit, 186,000 miles per second or 300,000 kilometers per second. So Saturn is about an hour and 23 minutes away from us right now, one-way light time. I'm a big sports nut. I tape a lot of games and DVR them, and the game is still exciting if you don't know the result and you haven't seen it. And no one's seen the Cassini last bits of science come back from Saturn yet. It's just about to cross the orbit of Jupiter. There's our graphic. And of course, Jupiter's in a little different position. So any denizens of the solar system at Jupiter or Mars, they'll know Cassini's fate and last bit of data before we will on Earth. So we're holding vigil here. We also have this display, kind of like a gauges in your car. This is the speed. Notice it's 63,000 miles per hour and climbing as we descend into Saturn's gravity well. And on the right side is the distance from the cloud tops, and that's just shrinking. It's going to head down over the next 37 minutes until we reach those cloud tops and say goodbye to our beautiful spacecraft out at Saturn.
And Todd, help us understand how the team will be monitoring this.
Yes, we've got a few ways. There's a display from, well, here's our radio signals. So this is the carrier frequency, and what I'd like to point out here, the peak in the middle, this is like the loudness or the signal strength, and at the Cassini frequency that it's talking. We have two displays, by the way, X-band and S-band. Those are just two different radio frequencies. So if you think in your car radio of tuning to different frequencies, that's like moving along the X-axis there, the horizontal axis. And we're getting a nice, big, strong, booming signal from Cassini on both those axes. But as we come into the atmosphere and turn away from Earth, our thrusters can't keep up anymore with the torques. Those will flatline, and that's when we say goodbye to Cassini. However, the key is to keep the data coming down to Earth and get those precious last few bits of science data from Saturn, our first sniff of the upper Saturn atmosphere. And boy, we're excited for that.
All right. Well, thanks, Todd. We will check back with you later. And one of the signals Todd showed you is part of a computer visualization tool we call Eyes on the Solar System. This JPL computer simulation software is based on real data from missions and is something you can download onto your own computer and use to follow along this morning. Just go to eyes.nasa.gov, download the app, and click on Cassini's tour. Here are two family photos we'd like to share. The top one was taken on June 21st, 2017. It's the Cassini team and alumni, and they filled the staircase on the mall here. Most of them are engineers. On the bottom photo was, and this one was just taken just a few days ago, it's the science team, and they were at Caltech. The team includes scientists from all over the world. Over the years, thousands of people have worked on this mission. In fact, there are so many members of the Cassini family, we couldn't fit all of them here at JPL. It's why there's a big crowd at Beckman Auditorium at Caltech in Pasadena, and that is where Cassini science team member Morgan Cable is right now. Morgan, what is it like out there?
Hi, Gay. Well, here at Caltech, you can hear it behind me, right? This is a historic moment, and I think the mood reflects that. But it's also like a family reunion. So we're here with our other fellow Cassini family members. We're seeing people we haven't seen in a long time for some cases, and it's just been wonderful to share these memories, to revel in the excitement. This is a celebration of an amazing mission and an incredible legacy.
Well, Morgan, you're one of the scientists.
Back to you at JPL.
You're one of the scientists out there. I mean, for you, you're probably being very reflective. What was one of the highlights for you of this mission?
For me personally, the discoveries at Enceladus have really revolutionized our view of where we might find life, or at least the conditions suitable for life in not only our solar system, but the universe. We've learned now that there are places where liquid water and the other ingredients for life as we know it to exist, chemistry and energy, exist in places like Enceladus. And that's thanks to the Cassini mission, which flew through the plume of Enceladus multiple times. This means that life may not only exist in the habitable zone around other stars, but now we can start to look for places like Enceladus or Europa elsewhere in the universe and extend our search to try to find that amazing discovery of life somewhere else.
All right. Well, we will be checking back with you, Morgan, later on the show. Thanks for that report. It is about 23 minutes past the hour. You're watching live coverage marking the final moments of Cassini on NASA TV. The Deep Space Network is awaiting the loss of signal from the spacecraft from DSN Antenna 43 in Australia. And let's go to Cassini's final hour display. At this point, the spacecraft has sent us data from about the 50-degree north latitude mark, and loss of signal should be coming about 32 minutes from now. Beautiful images from Cassini. The Cassini-Huygens mission made so many historic discoveries. Think about it. The Huygens probe sent back details of an alien world on Titan, a world that appears to be very similar to Earth. It found jets spraying water, ice, and organics from the south pole of Enceladus, revealing an interior ocean where there could be life. Over and over again, the mission revealed scientific wonders about Saturn, its rings and moons, and it hasn't stopped, at least not yet. With me now is Cassini project scientist Linda Spilker. This mission was determined to send down science right down to the very end.
That's right, Gay, till the very last second.
So Earl told us just a little while ago that overnight, the spacecraft sent back the last picture show, it's been called. Can you describe what those are?
Okay, well, let's go to the very first image, image A, as part of the last picture show. The first thing we did is we made a color mosaic, and these are just a couple of pictures from that mosaic. We'll stitch those together and have a beautiful image of Saturn plus the rings for the last time. If we go to image C, that's a movie of Enceladus actually setting behind the limb of Saturn.
And explain to me how the team decided to come up with this imagery and this selection.
Well, there's a lot of science in these images, so we wanted to do science. Oh, there's Enceladus setting behind the limb of Saturn, so we're saying goodbye to Enceladus and taking a last look at that particular world. And so we wanted to sort of do a survey, look at each of these key targets, collect picture postcards for our Cassini scrapbook. So these will be the last pictures that we'll put in our scrapbook. If we look at image D, that's a true color image of Titan.
Okay.
And you can see the lakes up in the north. Image F shows this in false color. There's a UV filter as part of image F, and the lakes really pop out. And you can also see that bluish haze at the edge of Titan. You know, Titan has this thick nitrogen atmosphere. We also took some pictures of the rings, Gay. If we go to image G, we're looking for propellers in this particular image, and you can just see a hint of it above that dark gap. If we go to image H, that's a blow up, and see that little two-armed propeller. It's that little bright feature just above the dark gap. There's a collection of ring particles that are large enough they're trying to open their own gap, and they create what looks like an airplane propeller. And they have fun names of aviators. If we go to image I, that was part of the sequence, we're looking at the tiny moon Daphnis. That's the Keeler gap. And you can see those crinkly edges along the gap. That's created by Daphnis awake as it goes through that system. And you can see the beautiful density waves, the interaction between the rings and the satellites, also as those bright features in our last look at the propellers. And finally, image J. This is an image looking at Saturn in a place where Cassini will be entering. So one of our last views, our very last pictures of Saturn. And you can think of Cassini as basically running a marathon. For 13 years, we've been running a marathon of scientific discovery, and we're on the last lap. And so we're here today to cheer as Cassini finishes that race.
Now, many of these images and what the spacecraft will be doing right now, all of this is unknown territory. The spacecraft has never been here before.
That's right. We're flying into Saturn more deeply than we've ever flown before. We have 8 of our scientific instruments on. The key instrument is the ion and neutral mass spectrometer. Basically coming in, we've oriented the instrument to sample the atmosphere of Saturn, which it's doing right now, deeper and deeper, until on the very final second, as Cassini fights to hold attitude, it'll send back those last very valuable packets of data. And who knows how many PhD theses might be in just those final seconds of data.
Right. We will have scientists and students poring over this data for decades to come, probably.
Right. And looking at the hydrogen to helium ratio to help us understand how Saturn formed, how Saturn's evolving, and who knows what else we'll see as we go into the atmosphere.
What great science leads it, still ahead. All right. Well, Linda, thanks for joining us.
Yeah, glad to be here.
You're watching live coverage of Cassini's final hour from the Jet Propulsion Laboratory. JPL is a NASA center in La Cañada, Flint Ridge, and Pasadena, California, and managed by the California Institute of Technology. Let's check out our display. We are now about just a little under 26 minutes from the end of mission. Well, the Cassini team considers itself a family, a team that works together and plays together. And here is one example. The Cassini Virtual Singers, they have a knack for putting a Cassini spin on just about any show tune. And I saw Todd Barber in that group. Todd, it is a very close-knit group and a multi-generational group. I mean, some people have spent their entire careers on this mission, and others are just starting their careers on Cassini. Todd Barber is standing by with one of the younger members of the team, guidance and control engineer Joni Stupik, who started her career with Cassini, right?
Yes, that's right. And I've been on since before launch, but it's so wonderful to have young engineers join the project. Welcome, Joni. And Joni is an attitude control engineer on the project. And can you explain what that means to our viewers?
Sure, absolutely. So I and my team are in charge of the orientation of the spacecraft. So we point all of the cameras and the antenna.
That's great. And you have a particularly important role this evening, right? Or this morning, I guess I should say.
Absolutely. So as Earl and Linda have both alluded to, we want to get every last possible second of information, which means our antenna needs to be pointed towards Earth for as long as we possibly can. As we enter into the atmosphere, Saturn is going to start trying to tug us away. So we want to hold the antenna as steady as we possibly can for that whole time.
And how do you do that?
We have little engines or thrusters that we use to hold us steady.
Wonderful. So that's, and basically we will lose the battle with Saturn's atmosphere.
We will. And if we go to the graphic here, we see the thrusters firing as we try and hold that antenna for as long as we can. And that will last for only about a minute until the thrusters are finally overwhelmed and we can no longer point the antenna.
Wow, that's amazing. But those precious seconds of science data are worth every thruster pulse we put on the
every second. Yeah, we're learning all about Saturn's atmosphere with all the instruments we can as we go in. So yeah, we want to point as long as we can.
So you started your career on this mission. How are you feeling tonight, knowing we have to say goodbye to our beautiful spacecraft?
It's definitely bittersweet. Yeah, I started my career. I was in high school when Cassini arrived at Saturn. So it's really exciting, and I'm really proud to have worked on such, incredible mission and be part of such a wonderful family. But it's going to be sad, I'm used to checking how the spacecraft is feeling every morning and things like that. So it'll be a little sad to not have that anymore.
I definitely agree there, and we're so grateful for your contributions and all the young engineers on the project, as well as the veterans that have been around since launch. Thank you, Joni.
Wouldn't be able to do without the veterans.
we got a few tricks up our sleeves still. So if we can head back to the radio science display and check and see, still looking good. So we have a strong X and S band signal. So as Earl mentioned, our fate is sealed. We've met our planetary protection requirement. We know we're going to impact Saturn and take care of that. The next thing that's important is to hold that signal as long as possible and get every last precious bit of science data. So far, so good, Gay. Back to you.
Thanks, Todd. Thanks, Joni. It is about 33 minutes past the hour, and the estimated time of loss of signal is 4:55 a.m. Pacific. The Cassini-Huygens mission has been an epic adventure around the Saturn system. It has sent home mountains of science data, stunning images. The spacecraft performed beautifully. The mission fulfilled its goals and then some. Members say they couldn't have asked for anything more.
This is Titan Launch Control. All the systems are go.
I've worked on the Cassini project for almost 30 years, and that's an entire Saturn orbit.
The beauty of Cassini is the design. It's the largest outer planetary spacecraft ever built. 12 different instruments. The Huygens probe, built by the European Space Agency. It's just a monumental machine.
2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn.
We turned the Cassini cameras down to look at the rings, revealing them in a way we had never seen them before. I remember coming back to JPL early in the morning just so I could be there and watch those pictures one by one come down. And I felt I could almost reach out and touch the rings that were right there.
We had been collaborating with the Europeans ever since launch to make sure that we had everything right for Huygens. The Huygens probe was dropped onto Titan. These are images from a billion miles away on the surface of Titan. They're boulders, they're pebbles. We're in a dry lake bed. And I still get goosebumps just talking about it.
Looking back at what we were planning to do in those first 4 years, we've gone so far beyond that.
We remapped our investigations to concentrate on the questions that Cassini raised.
2 of our instruments actually sampled the plume of Enceladus as we flew through, tasting the gas, measuring the particles in a way that we hadn't planned. Cassini has changed the paradigm of where we might look for life. That will be one of her legacies.
13 years of exploring Saturn. It really is just an awesome mission.
All right, well, joining me now is NASA Director of Planetary Science, Jim Green. Some of Cassini's greatest accomplishments came as big surprises, didn't they?
They did, absolutely. You know, one of the ones that's pretty spectacular, obviously, is Enceladus. Now, you may not really understand the importance of having a spacecraft with all kinds of instruments, including magnetometers and plasma wave instruments, but it was really discovered, the plumes, by a magnetometer. And so as the spacecraft was doing a flyby, what was happening is the plumes were being blasted out of the tiger stripes. They were being ionized, and they're loading down the field, dragging it by. And so the magnetometer saw the wave of the field in a place that they hadn't expected. And that gave a hint that something was going on and it needed to be looked at. And so then the next pass, they came up with the idea, well, let's look at it in backlight. And wow, there were the plumes. And that started then a series of new orbits and new trajectories to try to go through and taste the plumes and get even more details about what's happening at Enceladus.
And how does this discovery sort of change the way we look for life in the solar system?
Well, this is really a calling, if you will, of hey, you're going to have to come back because there's several things we know about life. One, it metabolizes. That means it takes in a liquid. It then uses that to extract energy, and then the liquid is used to extract the waste. But then it evolves, and then it also reproduces. Well, I can't measure any of those from our spacecraft other than going after the water. So once we see an area that has water, then we know that it has a possibility of being a habitable environment.
And transitioning to the other big story, also from Cassini, is another moon, Titan.
Oh, yeah, Titan. What a beautiful moon this is. You know, it's bigger than the planet Mercury. Its atmosphere is actually a significant one. It's twice the pressure that we have here on Earth. It's similar in the sense that it has a lot of nitrogen. In fact, it's dominated by nitrogen. But it also has liquid on its surface, which we know now is methane. And there's a hydrological cycle of evaporation, transport, rain, and then new lakes are forming in other locations on the moon.
And that's an incredible science legacy, but Titan also helped us with an engineering legacy as well.
Oh, absolutely. The concept of using Titan to do a gravity assist, swing bys, that then enable the spacecraft to get into different orbits is a fabulous concept, because while we're doing that, and here's the koosh ball, as we say, all these spectacular flybys allow us to look at Titan in detail. So from multiple flybys, we can get a global view of that moon, and we're using that same concept at Jupiter with another moon called Europa.
All right, well, before we go, I wanted to bring up the e-book, because one of the most fantastic things about this mission has been the imagery. Could you tell us a little bit about that?
Well, we really needed to make sure that we had wonderfully described and beautifully set images that were accessible to everyone. And after 450,000 plus images, it's so hard to pick. But we were able to go back in, get 100 beautiful images or more, and videos and all kinds of.
And there's a link where if you want to get it, you can download it off the internet.
NASA.gov/ebooks.
All right. Well, Jim, thanks for joining us. Thanks for taking time for us.
My
and
pleasure.
I know you want to get back into that control room.
Absolutely.
Thank you.
Thank you.
Well, we are a little over 10 minutes away from the loss of signal, so we will be focusing our attention to the control room very soon now. But before we do, let's take a moment to chat with JPL Director Mike Watkins. So, Mike, how are you feeling?
Well, first, good morning.
Yes, very early morning.
We always tend to do these events somehow at 3 in the morning or 5 in the morning.
Why did they do that?
But, it's kind of a bittersweet event for all of us, I think. For me personally, it's more sweet than bitter because Cassini's been such a fantastic mission. But I think, one of the important things about these events is to celebrate the incredible hard work, the decades of hard work of the team that designed, built, and operated Cassini. And that's really, right, the heart of the spacecraft is really the people that worked on it and the people that have been operating it. And this is a great time to celebrate that level of dedication, that devotion, to work on something for 10, 20, 30 years. That's sort of unparalleled in human history.
So how do you think Cassini will be remembered in the science books?
Well, I'd say most of the science books, most of what we have in science books about Saturn come from Cassini. Right. So it will be long remembered. I mean, if you look at almost everything we know came from Cassini about Saturn. But I think one of the greatest legacies of a mission is not just the scientific discoveries it makes and what you learn about, but the fact that you make discoveries that are so compelling that you have to go back. And that's really the part of what makes the end of Cassini sweet, is that the discoveries are so compelling that we have to go back. We will go back and fly through the geysers of Enceladus, and we'll go back and look at Titan, because it's just the Cassini findings are just they're just groundbreaking.
But the way missions are, one mission sort of sets the footsteps for the next mission. So what's coming up next after Cassini?
So one of the things we've learned about the outer solar system is how much water is there. So we used to think that most of the water was here in the inner solar system. Here on Earth, for example, the habitable zone, Goldilocks zone between Venus and Mars, where we are. We now realize that there's a lot of water in the outer solar system. So Europa, for example, the moon of Jupiter, Enceladus. And I think what you see compelling about the outer planets is to go back and look at those ocean worlds in great detail. Fly through the geysers, try to drill down through the ice, take a look at the composition of the ice. And as Jim Green noted, are these habitable places? Are these places where there could be life? And so we here at JPL and NASA, we have plans to go back to many of these ocean worlds, as many as we can. The next one up is a multiple flyby of Europa. We call Europa Clipper, where it'll be in orbit around Jupiter and fly by Europa 40 or 50 times, and taking a very close look at that ocean and from above the ice, of course, and the composition of the ice. And then later we'll make our way to the other ocean worlds.
Ocean worlds are the things to look at right now, it seems.
Absolutely. The search for life is one of the compelling threads for NASA and for the Science Mission Directorate and for JPL. We're looking for life in our solar system, and of course we're looking for life outside the solar system. We're looking for exoplanets and other Earths. But the ocean worlds look like an incredibly compelling target.
All right. Well, thank you so much, Mike, for coming by and joining us. I know all the guys want to get back in there in the
Absolutely.
Control room and be there for the moment.
The last few minutes.
All right.
Thanks, Kay.
Thank you so much. You're watching live coverage of Cassini's final hour from NASA's Jet Propulsion Laboratory. JPL is located in La Cañada, Flint Ridge, and Pasadena, and managed by the California Institute of Technology. Let's take a look at our last hour display. Our display shows that we are just over 7 minutes away from the end of mission. And it's now traveling about 75,000 miles per hour. So Cassini is traveling rapidly towards its end of mission.
For all the beauty and the exotic features that we found, those are places that startle and amaze, but not a place where you can live. And I think it gives you a perspective on the Earth and what a wonderful place it is, and more impetus to perhaps take care of it.
We are getting close to time, and at the time where we should lose that signal. Folks are watching the radio science display right now, so let's go to Todd and Joni in Mission Control.
Hi, Gay. Well, 6 minutes to go till we're 6 feet under, so it's going to be hard to say goodbye here. Radio display still looks great, as we just saw on screen. Mission Control, I hear a lot of buzz in the room about the thruster cycles, because the thrusters are firing. We're still outside the atmosphere, and they're just keeping deadbands, keeping that pointing on Earth as long as possible. So things aren't too crazy yet, but once we hit that atmosphere, things happen super fast. So let's look around the room.
ACS is nominal. We're in low rate mode, and we're waiting for high rate mode transition. Copy, thank you.
So that was
ACS fault protection systems lead. Go ahead, system lead. Just going to get a quick subsystem status, please. AECS fault protection is nominal. Copy, thank you. Thermal systems lead. Thermal devices subsystem is nominal. Copy, thank you. Power systems lead. Power subsystem is nominal. Copy, thank you. System fault protection systems lead.
System fault protection is nominal. No fault protection activity.
Copy, thank you. CDS systems lead.
CDS is nominal. We have 2 frames buffered.
Copy, thank you. Telecom systems lead. Telecom is nominal. Good, SNT. Copy, thank you. Radio science systems lead.
Radio science is nominal. Signal levels are nominal. The residual frequency is starting to increase.
Copy, thank you. Propulsion systems lead. Pressures and temperatures are nominal. Propulsion is nominal. Copy, thank you. Mission planning systems lead. Mission planning is nominal. Copy, thank you. Flight director systems lead. Everything is nominal.
Copy. And Ace copies.
Thank you, Ace.
So what we just heard was the room going around and checking all of the subsystems. So far, all of the subsystems are nominal, about 4 minutes, 3.5 to 4 minutes away from the end.
Joni, I heard a comment there that we went from low rate to high rate control. Can you comment on that?
Sure. So we have our computer that's controlling our pointing has different modes, and it's smart enough to know when we start having to fight a little harder. So we heard that the computer acknowledged that we start having to fight a little bit.
Okay, thanks. We were remarking earlier, it's incredible this entire spacecraft runs on 600 watts of power. How much power is that?
Yeah, about half a hairdryer.
Wow.
That's all we got right now.
I won't even talk about how little fuel we have left. It's about 1% plus or minus 2%. So that's one reason we're heading into Saturn's atmosphere tonight. Under 3 minutes now. We should definitely emphasize we don't know exactly when we'll lose signal. It depends on the Saturn atmosphere and how well the thrusters fight. So stay tuned.
And we're
Radio signal looks wonderful. X-band and S-band, 2 different radio bands, still getting the signal from Cassini.
We're approaching about 10 degrees north latitude on Saturn. We're 3,000 miles from the cloud tops.
I remember seeing we were going to hit the atmosphere about 77,000 miles an hour. I see we're close, so. 2 minutes and counting.
Oh, we're starting to exit the...
Systems, this is ACS-1.
Go ahead, ACS.
We're still waiting for transition to high rate mode, but it looks like we're going to start accumulating thruster on time at a higher rate now, and our attitude control error is starting to be more active.
Copy.
That means we're just starting to sense the atmosphere, right?
Yep. We can start seeing the spacecraft starting to lose the battle with the atmosphere.
Systems ACS-1, we just had the transition to high rate mode, and with this, we're going to start seeing thruster on time accumulating very quickly, and the deadband is going to clamp down to 0.5.52 millirad, and we are in the atmosphere.
Copy, thank you.
Roughly 1 minute to loss of signal.
Systems, this is Nav. Go ahead, Nav. We can confirm what AACS just told you. Copy, thank you.
We're just starting to see the thrusters fire more and more. Yeah, everyone can.
Radio signal still holding. 30 seconds.
Systems lead, mission planning.
Go ahead, mission planning.
Spacecraft has just crossed 10 degrees north latitude, altitude 1,000 miles.
Copy, thank you.
Systems, ACS-1.
Go ahead.
With the additional thruster on time, we're going to also see the deadband start riding.
Copy.
Oh, yeah.
We've crossed our 0 time.
correct?
We have lots of signal at X-ray band and Sierra band.
Project manager, flight director.
Go ahead.
Okay, we call loss of signal, loss of X-band at call loss of signal at 115546 for the S-band, so that would be the end of the spacecraft.
Copy that. Project manager on FSO Quard. Maybe a trickle of telemetry left, but just heard the signal from the spacecraft is gone, and within the next 45 seconds, so will be the spacecraft. I hope you're all as deeply proud of this amazing accomplishment. Congratulations to you all. This has been an incredible mission, an incredible spacecraft, and you're all an incredible team. I'm going to call this the end of mission. Project manager off the net.
Very close to right where we took.
also, just a short time ago, Julie Webster, the Space Operations Team Manager, and Program Manager Earl Mays called it the end of mission for Cassini. It came at about 4:55 as predicted. Let's go now to Beckman Auditorium and check in with Morgan Cable. She is with Cassini interdisciplinary scientist Jonathan Lunine to find out how the scientists are doing and the team is doing down there. The mission is certainly not over for them because now there will be tons of data for them to be poring over. Morgan?
That's a very good point, Gay. There's going to be lots of data to analyze for years to come. Jonathan, how are you feeling right now?
I'm actually breathing again, and I feel sad, but we felt sad the whole week. We knew this was going to happen, and Cassini performed exactly as she was supposed to, and I'll bet there's some terrific data on the ground now about Saturn's atmosphere.
I'll bet you're right. What was your favorite memory of Cassini? Well, or share a story, just anything that comes to mind.
My two favorite moments were both having to do with Titan. One was seeing the seas of Titan for the first time from the radar on Cassini, and the other was seeing the surface of Titan from the Huygens probe, sitting with 30 other people in a trailer in the middle of Germany in the middle of winter. It was cold and dark, and there were the first pictures of gullies on the surface of an alien world.
That had to just blow your mind.
It did. I was screaming. So was everyone else.
Well, I think the mood's been a little bit more somber now, but there was applause right near the end. I think this is a celebration of Cassini's life and Cassini's legacy, and we should talk a little bit about the future. What do you see next for the Saturn system?
Well, what I would like to see next for the Saturn system is that we go back there. And there's so many things that Cassini has given us in terms of a legacy to explore. Enceladus and the possibility of life, Titan and its amazing atmosphere and lakes and seas and hydrologic cycle, Saturn and the rings and the mysteries of what lies beneath the clouds. There's an awful lot that Cassini has said to us we must go back and explore.
Yeah, there's a lot left to do in the Saturn system and elsewhere in the solar system as well.
Yeah.
Well, this has been an international mission and an intergenerational mission, right? It's been such a joy for someone like me to be able to be mentored by veterans like you. In terms of following on Cassini's legacy and mentoring the next generation, what do you see in terms of next missions coming up, being able to bring in the next generation of scientists and engineers?
First of all, I'm very, very confident and optimistic about the next generation because I can see that the experts are here already. So we will be well served in the future. Of course, NASA is going back to Europa with the Europa Clipper, which is very exciting, and the Europeans are doing JUICE to the other Galilean moons, and there are a number of concepts out there for going back to Enceladus and Titan and to Saturn. We don't know if any of those are going to happen in the next few years, but we'll see. There are lots of ideas. The important point is that Cassini has got to be a jumping off point to even more exciting exploratory missions. We can't let it stop at this point. We have to keep going on. We will in the Jupiter system. We need to go back to Saturn. We need to go to Uranus and Neptune. We need to do the whole outer solar system.
We need to. The outer planets, I think one of the amazing things that Cassini has shown us is that it's not a boring, cold place. It's dynamic. It's so incredibly varied. Just the differences in the moons of Saturn alone. It inspires us to want to go back and to learn more.
Yeah, you know, 40 years ago, Voyager 1 was launched. And it was Voyager 1 and 2 that broke open the outer solar system for us, told us that this was not a cold, dead, gray place. And then Galileo and Cassini followed on and showed us what really amazing things are going on in those systems, and that there might in fact be places for life to exist in Europa and Enceladus and Titan. And I have a poem I want to read to you as well at some point. Is this a good time?
I think it's a great time.
Okay. You know, a lot has been said about Cassini already and the end of the mission, but I think that the
best I can do to leave this celebration of Cassini's End is to read a bit of a poem by Swinburne, On the Verge, which was a nautical poem about death and dying, sailing on the sea as a metaphor for death. And so I'm going to read the last few lines of it, and I've changed one of the words. It'll be obvious. Ah, but here Cassini's heart leaps, yearning toward the gloom with venturous glee. Though her pilot eye behold nor bay nor harbor, rock nor shoal, from the shore that hath no shore, beyond it set in all the sea.
That's beautiful. You had to do that, didn't you?
I did. Sorry, Morgan.
Thank you, Jonathan, for everything.
Well, Morgan, the future is in your hands and the hands of your generation, and this was a moment of transition. It was not the end. And so let's go forth and explore the solar system together.
All right. That's a beautiful sentiment. Well, with me now is NASA Associate Administrator for Science, Thomas Zurbuchen. Dr. Zurbuchen, what was your reaction being in that control room?
Well, I was just overwhelmed with just understanding how professional this team is. You know, like during the entire time, this was clearly emotional for everybody. The Lucky Peanuts were there, but there are a lot of Kleenex, and there's a lot of use of Kleenex, but everybody was so professional to the very end, and I just saw it happening. You know, it went so fast. You know, somebody was shouting out, wow, we're struggling with Z-axis, and oh, it's gone. And I just saw that team holding together till the very end. Just really, it's all about teamwork with this mission, and it showed in the last seconds.
It truly did. And your feelings about this, what sort of legacy do you think this mission leaves?
You know, I really do think it rewrote not only what we know about the outer solar system, but how we think as humans about ourselves. You know, these worlds that it found, we never knew were there, are changing how we think about life itself. And so for me, that's why it's truly a civilization scale mission, one that will stand out among other missions anywhere.
And how will it impact future ideas and future missions as we plan new things?
You know, some of the hardest questions to answer are questions like, is there life out there? And this mission really has redefined that. It will affect how we think about that question. So, of course, we're tackling that at NASA with a multitude of missions, looking at Mars, trying to bring samples back, but also looking at Europa, looking at these outer ocean worlds and finding these worlds all over the universe, all over our galaxy. Every, there's thousands of these exoplanets and, Saturn-like, Jupiter-like kind of exoplanets that we're discovering, and we're thinking about that in a totally new way.
And so the thought is people are clamoring to go back. Will that be difficult to do, to be able to envision another mission to these places soon?
It's always very difficult, right, to do this, because these machines are so hard to invent. To go back and, for example, take the next step on Enceladus, we want to really think what that will take. Now, there's great ideas already out there, and perhaps some of these ideas will come to fruition relatively early. I don't know, but we will really start thinking about this and start talking about it in the science community overall. I mean, we encourage them to really start, making plans so we can create a consensus as to what direction we want to go at. Yes, we want to really go back. This is such a wonderful system. We don't want to leave it alone.
Right, and such a beautiful one, and it's affected so many people. Dr. Zurbuchen, thank you so much for sharing this moment with us. A very special one.
Thanks to the team.
Well, the Cassini-Huygens team was a multi-international team, and in just a few moments from now, we will be speaking to members of ESA and OSSI about their feelings about this mission. As we told you earlier, Cassini-Huygens was a multinational endeavor from the very, very start, a partnership between NASA, the European Space Agency, and the Italian Space Agency. This is an equally proud moment for ESA and OSI. And the ESA Director of Science, Alvaro Jimenez, joins us, and the President of OSI, Roberto Battiston, are here to share this historic moment. Thank you so much for coming. Was this something that you decided you wouldn't miss it for the world?
Of course, we couldn't miss it because we knew this moment was going to come. It's a little bit sad because we wanted to delay it as much as possible and get as much science as possible, but we knew it was coming. And that sense is sad, but it's also very nice to see that we have opened the possibility for the future science also, and for the scientists to work on the data that Cassini has collected, but also as an example, and I think we have to build on this cooperation between the US and Europe in ambitious missions like this. We are very proud of having worked together, and we have to make sure that we continue this way, because together we can do much better than separate.
More. And Roberto, your feelings, I mean, to be a part of this.
I mean, it is a very historical moment, and being part of that is really something very emotionally intense. I was not there 20 years ago when this started, but I know the story of all my friends and colleagues, and Cassini demonstrated that we can do that. We can create the conditions for the international collaboration, a mission which can operate for 20 years, which can learn a tremendous amount of things for the future, is one step, a gigantic step toward the future, and I really wish and hope this is not the last one, but it's only the first one of a series.
Were you surprised at how long this mission has lasted? And the amount of information and science that it has brought back?
Not so much about the length. I think we all dreamt about it, but the discoveries and what we have found in the Cassini system, in the Saturn system, are simply amazing. We were surprised by that.
And ESA's role with Huygens and working on Titan. I mean, what was the high points for you?
Well, for me, Huygens was getting to Titan. We landed there in 2005. But the whole purpose was to understand the atmosphere of Titan, to analyze the atmosphere, which is a prebiotic atmosphere full of nitrogen and methane and these kind of elements, which is what we thought that these bodies outside in the outer part of the solar system were before life could appear, and we wanted to analyze that. But then we found that we could even land. When the mission was designed, we thought we didn't know how the surface was.
That's
we didn't know if it was going to sink or land or whatever.
And it was alive for some time when it landed.
Was alive, and that was amazing because also we could see first this was the furthest away landing ever of a human-made probe, but also we found a landscape totally unexpected of Titan, something similar to Earth, actually, with lakes and rivers and mountains, and very appealing. But
well, anyone who's watching right now, I just want to say thanks for being here. I'm gonna shut this down. Peace.
And Roberto, let's talk about OSI's role and the high gain antenna. So often the project relied